So last time we saw that heaps can be used to implement a priority queue. So remember that in a priority queue, there are two basic operations: insert, which adds an element, and delete max. So in a priority queue, each element has a priority. So when you remove an element from the queue, you must remove the one with the highest priority, not the one that was inserted earliest. So in a normal queue, it's first in, first out. Whereas here, you look at all the elements that are there and you take out the one with the highest priority. Now you could dually also take out the one with the lowest priority, in which case it would be delete min. So we could implement this in an efficient manner using heaps. So heaps are balanced trees, balanced binary trees, in which insert and delete max or delete min can both be done in log n time if there are n elements currently in the heap. And then to start with, you must make a heap. So we saw that you could take a list of n elements and construct a heap from it in order n time. And the main advantage of working with heaps is that because of the balanced structure, remember that a heap is filled layer by layer left to right, you can now index the heap starting with the index 0 for the root, 1 and 2 for its children and so on, and then by just doing a simple index calculation. If you remember 2i plus 1, 2i plus 2 will give you the children of I, and if you take I minus 1 and divide by 2 integer, you will get the parent of a node. So we don't actually have to maintain a graph like structure, we can just work with a list or an array and just move around in the array using the simple index arithmetic to get from parent to children. So now that we have this heap in which we can maintain these values so that we can extract the minimum or the maximum in logarithmic time and also insert in logarithmic time, what more do we need to use it in an algorithm? And which algorithm are we actually going to use it in? So the reason that we started looking at heaps to begin with is because of Dijkstra's algorithm. If you remember in Dijkstra's algorithm, what we do is we start with a single vertex and then we keep updating the distances to all the remaining vertices based on the values we have already visited. So initially we don't know anything about any distance, then we start with one vertex, it is at distance 0, then we update the values of its neighbors, then pick the nearest neighbor, go to that, update the values of its neighbors and so on. So in this way we sequentially visit all the vertices in the order of their distance from the starting node. So we have to maintain this two dictionaries, okay, one which tells us which nodes have already been visited and a second one which tells us how far it is to each unvisited node, right. So when it's visited, the distance becomes frozen. After the node is visited, you don't find a shorter distance. That was the proof of Dijkstra's algorithm. But till it is visited, you will keep finding shorter paths because you will discover new paths to it. So you initialize this distance dictionary to infinity, and then you initialize the start distance of the starting vertex. So this is this distance of s to 0, and then you keep finding the smallest unvisited vertex, right. So you call that next vertex, the smallest distance unvisited vertex. You set its visited status to true, and now this was the problem that you have to actually recompute the distance for all the neighbors of this new vertex, right. So you have two problems here. You have to find the unvisited vertex and you have to update all the distances, right. So the first bottleneck is to find this unvisited vertex, and what we said was that there is no simple way to do this because the vertices are not maintained in any particular structure, right. So we have to just scan all the vertices and check. So this is what we do here, right. So we basically run a loop saying take every vertex that is not visited and find the one with the minimum distance, right. So we really have to do an order n scan in order to find the next vertex at every iteration, and there are n iterations because we are finding the vertex to finding the distance to n vertices. So that's what we got for our n squared worst case complexity for Dijkstra. So now an obvious suggestion is that we can use a min heap, because what we want is we have a collection of distances, right, and we want to take from this collection the smallest value or a smallest value of more than one. So remember that this min actually gives us a collection of values which could have the minimum distance, and then we actually take this next vertex list and pick the kind of smallest one in that, right. So how do we do this? Well, we should be able to keep a min heap. So if we keep a min heap, So we keep the distances in a min heap. Now why do we need a min heap? Because we need to delete the minimum, not the maximum. So you take a min heap, remove the smallest vertex, and what we have just seen is that this delete min should always work in logarithmic time. So therefore, if we do this n times, we will have an n log n cost for finding the next vertex over our n iterations. Right? But there is still one bottleneck, which is this part. Right? The bottleneck is not so much to do with the complexity of the loop here, but the fact that we have to do something on the heap which we have not described how to do. So we have to take the elements on the heap, which are all the unvisited vertices, and we have to change their values, because the values on the heap represent the distances, and when we visit a new vertex, the main property that we have to ensure is that now we recompute the distances from this new vertex and see if it is smaller than the distance we already knew, and if it is smaller, then we reduce it, right? So we take the minimum of these two distances, the new distance and the old distance. But so far in a heap, we haven't seen any possibility of modifying a value, right? We know how to insert a value, we know how to delete the maximum or the minimum, in this case is minimum, but how do you take an arbitrary value which, so if it was the minimum value that we wanted to change, it would be easy. You delete it and then you insert the new value. But we are changing some value which is neither the minimum nor is it a new value to be added. We have to take some arbitrary value in the middle of the heap and change it. So this means that we cannot directly use a heap for Dijkstra's algorithm without making some additional observations about how the heap works. So what we are going to see now is how to update values in a heap. Right? So what we have seen earlier is how to insert a new value into a heap, add a node, delete the minimum value, remove the value at the root, remove one node at the bottom, and then readjust the heap. And now we want to modify value. So supposing we take this value 54, right, and we want to change it to 35. So if we update it to 35, then what happens is that we could, because now it's a min heap, right? So each value has to be smaller than its children. So if I reduce this from 54 down to 35, right, it is definitely going to remain smaller than its children. 54 was already smaller than 68 and 59. I have taken 54 and made it 35, right? So there is no problem with its own children. Remember, the heap properties are all local. I only have to look at a node and its children, and then inductively it shows that the smallest value must be at the root, right? So now there is no problem here. But what about here, right? So here earlier 38 was smaller than 54 and 47, but because I have reduced 54 to 35, I have a violation of the heap condition with respect to the parent of the node that I am changing. So if I have a violation with respect to a parent, this is something that we have seen before. This happens typically when we insert a new node. When we add a new node here, it could very well be something like 11, right? And it might be smaller than 47, and then we have to do some work. And the work that we do is to swap it with its parent. So we can do the same thing here. If we find we reduce a value, we check with its parent, and then we exchange, right? So similar to insert, we exchange, and remember, similar to insert, this is guaranteed to be smaller than this, because 35, the reason I am swapping it is because it is smaller than what its parent was, 38, but that parent was earlier smaller than 47 anyway. So by moving a smaller value up, I am not going to violate the heap property on the other child, right? Now it so happens that it stops here, but supposing it had been 25, right? Then 25 would have been exchanged one more time, and I would have got 29 here and 25 there, right? So this is very similar to insert, except we are starting from not the bottom as we did in insert with a new node, but somewhere in the middle of the heap. So whenever in a min heap we reduce a value, it might need to be bubbled up the heap, right? Swapping with its parents along the path to the root. And of course the other problem, the other kind of update we could do is to increase a value, right? So supposing I now take this value, right, and I make it 71. Now because in a min heap it must be smaller than its children, the problem cannot come with the parent. Of course this is a root node, but supposing I take this 31 for example and made it say for instance 81, right? So this cannot create a problem with its parent because it was already bigger than its parent, because the parent was smaller than it, So 81, 31 was already bigger than 29, so 81 will remain bigger than 29. But the problem could happen here, right? So 81 now becomes bigger than 61. So let's stick to the example that we have. So let's not fix this node, but fix 29. So 29 we change to 71. So like we did, now this is similar to the delete min. This is what happens sometimes when we delete the minimum and we put a big node, a big value up there, and then we have to move it down, right? So we move it down to the smaller of its children. So 29 has to be exchanged with either 35 or 31, but we want to move the smaller one up so that the heap property is fixed there. So we will exchange it from 71, we will exchange it on the right hand side. So we have done an exchange here, and now 71 is still not in the right place because it is still bigger than 61. So I have to do it one more time, and then eventually, so 71 has come all the way down here and these two values have gone up, right? So this is very similar to what happens when we delete the top element, the root element, we delete the minimum. We would take the value which is at the last leaf and move it there, but that could be an arbitrary value, need not be the new minimum. So then it has to bubble down, right? So these two update operations are exactly like what you would do for the two other operations that we know, insert and delete min, right? So in this case, reducing a value behaves like insert in terms of the updates you have to make, except you start from the middle of the heap. And similarly, increasing a value causes operations like delete min, except you start somewhere in the middle of the heap again. So both of these updates are therefore log n, because we know that insert as a whole is log n. So this is a special version of insert in a sense. Similarly, delete min is log n. So now if that is the problem that we had, how to do that? So remember, the bottleneck that we had in Dijkstra's algorithm was that at this point we had to update all these things, and the question was, how do we do it in a heap, right? Because we didn't know how to do it in a heap. So what we claim now is that you can do it in a heap in log n time, right? But there is still a small problem, which is when I say change 54 to 35, what I would really typically have is I'll have in my graph, right? I will have a vertex, say I will say that this is V7, and I will say update the value of V7 from 54 to 35. So I am talking about the values with respect to the nodes in my original graph. Now these values have been moved around and they are living somewhere in this heap. So the question that I have to now resolve is, how do I find that value 54 that I wanted to change in this heap? So I have a node in my graph, right? And I have a distance to that node, and that distance is currently sitting in the heap in some position based on all the previous operations that have happened. Now I want to make this distance something else, I want to reduce it. How will I go into that heap and find where this distance is, right? Because unfortunately this heap has no other particular value, right? Notice that in this min heap, for instance, I have values on the left which are smaller than the values on the right, but I could also have values on the right which are smaller than values on the left. So there is no particular order once I go after the this minimum property within the neighborhood. There is no global property which says where to find. So finding will become an exhaustive search, right? So if I have to find that value, I will be in trouble. So in order to keep track of that, we have to actually maintain a kind of separate index, okay? So since we are talking in the context of graphs like Dijkstra's algorithm, I will assume that the original values that I am keeping track of are the vertices, right? And these vertices live in the heap at some positions. Now there are n vertices and there are n positions. So there is a one-to-one map, right? Each vertex is in a unique position and each position has a unique vertex. So I want to keep track of this map, right? And you can think of it as a dictionary, okay, which says, given a vertex, what is the position of the node? Given a node, which vertex is here? So it's convenient for us that the vertices are numbered 0 to n minus 1 and the heap positions are also numbered 0 to n minus 1. So let me kind of represent that same heap in slightly more detail. So let us assume that the blue numbers, right, which are in the nodes, represent the vertex number, and the black number is the distance. So it's a min heap with respect to the black numbers. 29 is smaller than 38 and 31, 31 is smaller than 84 and 61 and so on. But these vertices are like this. So I have this mapping here which says that vertex 0 is at position 7. So if I want to update vertex 0, I will go 1, 2, so remember that I will number a heap from the top, 0, 1, 2, 3, 4, 5, 6, 7, 8. So these are my heap indices, which are just determined by this top to bottom, left to right order. So it says 0 is at 7, so I just have to go to heap position 7, and indeed I find that the vertex there is 0, right. If I look at vertex 6, for instance, it says at position 6, and indeed at position 6 I have 6. So this is my vertex to heap. Given a vertex, if I want to update vertex j, I look at this V to H dictionary and I look up the value for key j, and it will tell me which node in the heap has that value. But then I also need the reverse, because I need to kind of, when I exchange, I will go to a new position and I need to know which vertex I am moving, right, so that I can update this thing. So I have the reverse thing which says at position 3, right, which is here, at position 3, the vertex is 1, right. So this is a heap to vertex map. It tells me if I am at position k in the heap, which vertex I is stored in that position k. Right. So if you go through this, the reason I have put these blue vertex numbers on the heap is that in the normal course of things, of course, you would only keep the distance. But here I don't have the graph. This is a kind of imaginary example. So I am just claiming that this was the graph, right. So the graph had these vertices 0 to 8, and at some point these were the distances. So I am just keeping the vertex names to just show you that this mapping is actually consistent. So now the problem has to be to update this. So when I come to update, supposing now Dijkstra's algorithm says change the distance for 1, which was 54, right, change it to 35, right. So then I know that I am going to be doing something with this entry, right. So first I look at this vertex to heap, and I find that the node 1 is at position 3. So remember, this is position 1, 2, 3, right. So 0, 1, 2, 3. So now I know what position I have to update, and because it is a heap, I know its parent is at position 3 minus 1 by 2, which is 1, right. So I know this position. So I look at position 1 and I decide I have to swap because 35 is smaller than 38. But what is at position 1? This is where I need the other thing. I go to position 1 and I see that what is there is node 5. So then I have to go here and look at node 5, right. So that is going to change. If position 1 is swapped with position 3, where node 5 is going to change from 1 to 3, right. And this is also now going to change, because what is at 3 is going to become 5 and so on. So basically after this exchange, I have to make this update in these two. So I have to exchange the values, but exchanging the values in the heap also entails updating these entries. So the entries which corresponded to vertex 1 and 5 get swapped from 3, 1 to 1, 3, and the entries corresponding to positions 1 and 3 in the heap get swapped to vertex 1 and vertex 5 from 5 and 1, right. So every time we make a swap in our heap operation, we have to update this, but this is just because they kind of reference each other, it is just a constant number of lookups. I go from V to H, I get the value, I go back from H to V, and then I update both the corresponding pairs, right. So I do these two swaps in this V to H and H to V array, and I am done. So this then is how you do this Dijkstra's algorithm with a heap, right. So first of all, you use a min heap to keep track of the distances of the unvisited vertices, but because you have to do this update, which behaves like insert or delete min. Now in Dijkstra's algorithm, you are always going to reduce, right. You are always going to reduce the value. So it is always going to behave like insert. So it is always going to become smaller than perhaps its parent and go up. You are never going to update a value in Dijkstra's algorithm to become bigger. So all of Dijkstra's algorithm updates are going to be of the type where you reduce the value and therefore you move up, but still whatever you are doing in the heap in terms of updating, you have to first find that element, and for that you need to keep track of these extra index dictionaries telling us where a vertex is in the heap and which point in the heap, which vertex a position in the heap points to. So now that we have that under control, so now we do have a heap based implementation of Dijkstra's algorithm with this extended version of a heap, right. So this extended version of a heap, right, first it allows us to identify the next vertex to visit in logarithmic time, because it's basically this min heap. So I just have to do a delete min. Now updating the distance, because of the way we said the update works in the heap, is log n times per neighbor. So I have to take the vertex that has just been visited and update all its neighbors, because those are the only ones for which the distance has now changed as a result of this becoming visited. But if I am keeping an adjacency list, as we saw before, then I can efficiently enumerate its neighbors by just walking down the list. So the work I will do for a given neighbor is proportional to the degree of that neighbor. So therefore, over all this, I can expect that if I visit n vertices, each time I have to choose the vertex to visit, and that takes log n time. So I take n log n time to identify the sequence in which I visit vertices. And when I visit a vertex, I have to update its neighbors, which takes log n time per neighbor. But if I add up like we have done before for breadth first search and depth first search, if I use this degree property that I am using the adjacency list, so the total number of updates I am making is proportional to the total number of edges, because I will update only across an edge, in particular in Dijkstra only once, because from the visited site to the unvisited site. I will never go back, because I will never update an unvisited neighbor, right. So I will make as many updates as there are edges, so that's going to take me m log n times. So m is the number of edges. So n log n time for finding the vertex to visit, m log n time to do the updates. So this gives me an overall time of m plus n times log n, right. So remember that m plus n is roughly the size of our graph, right. It's the number of edges plus the number of vertices. So we saw earlier that when we claimed that, say, BFS and DFS were linear time, it was order m plus n. So this is really something like the equivalent of n log n. We have already seen that in when we use, for instance, in Kruskal's algorithm, if you use union find, we got a similar complexity, right. So this is more or less the best you can hope for a non-trivial algorithm, because we can't do it in a single linear scan, but we can at least do it in a kind of m plus n times log n type of scan. So there is something else interesting that we can do with a heap. So one part is to implement Dijkstra's algorithm, okay, and get an efficient solution, but we can also sort a list using a heap. Now you can realize that heap is somewhere in between an unsorted thing and a sorted thing, because at least it has found the maximum or the minimum, right. So you are not in a totally unsorted case, but you are not in a totally unsorted, you are not in a fully sorted case either, because the values outside the root are in an arbitrary order. So if I want to actually sort a list, what I can do is first build a heap, and as we know, building a heap takes linear time. So I can start with an unsorted list and build a heap, and now I can repeatedly find the extreme element. So let us assume it is a max heap, for instance, right. Then I delete max, I have got the maximum, right. So it's a bit like a clever way of doing selection sort. If you remember, this is what we did in selection sort, right. We scanned the entire stack of papers which we were given by our teacher to grade after grading. We took the maximum one and put it aside. Then we went through the whole stack again, took the second maximum one and put it away. Now the thing is that instead of doing this in an arbitrary way, we first built a heap out of these papers. Then delete max gives us 1. But once I delete max, magically the heap reorganizes itself, so the maximum is again at the top. So I keep deleting the maximum n times, and after I delete it n times, I have extracted the elements in descending order, right. So therefore I have actually found a sorted sequence corresponding to the original sequence. And how long did it take? Well, it takes me log n times for each delete max, so in n log n time I have sorted, right. So where do I keep the second stack? This is always a problem, right. So we saw that in selection sort, we would move that extreme element to the beginning and then sort from the second element onwards. In a heap, we can do the same thing, except we can turn it around and move it to the end, right. So we can take a heap which has positions 0 to n minus 1, and remember, when I have 0 to n minus 1, I think of it as 0, 1, 2, then 3, 4, 5, 6 and so on. So the logical thing we said when we delete an element is to delete the last element. So the heap shrinks by 1 means that the positions go from 0 to n minus 1, they become 0 to n minus 2. So this position henceforth is outside the heap. So this is a position that's available to me. So the value that I just deleted can go here and it will not be touched again, right? So we can store the maximum value at the end of the current heap at position n minus 1, because the heap is now lost that value, so it only exists in the space 0 to n minus 2. Then I delete from 0 to n minus 2, then the n minus 2th position will become free. So whatever value delete max gives me, I can put it there, and I have all the elements again in a heap from 0 to n minus 3. So I can keep doing this, and in this process I actually get an in place order n log n sort. Right? So I take a list in some sense, I heapify it in place, right? Because the heapify operation also just did some exchanging and put it in place. Then I do a delete max and I take that value and put it at the end. I take the next value, put it at the end, and so on. So I have an order n log n in place sort. So remember, the only other order n log n sort that we have is merge sort, and it's not in place because the merging operation requires us to create a new list, right? So in that sense, this is an improvement on merge sort. Okay, so to summarize, we have seen that you can take this heap which has insert and delete min, delete max, depending on whether it's a min heap or a max heap, and we can extend it to have this update operation, and this update operation will also work in logarithmic time. But in order to use this update operation, we need to be able to decide which position to update. So if you need to point to the position and say update this position, we need a way of going back and forth between the values that we are keeping track of and the values in the heap. So we said that we will keep these two dictionaries, which gives us this one-to-one mapping between the values we are, like the nodes, the distances of the vertices and the nodes in the heap, right? So with this extended notion of a heap, Dijkstra's algorithm came down in complexity from n squared to m plus n log n. So the other algorithm which is similar to Dijkstra's algorithm is Prim's algorithm for the minimum cost spanning tree. So we've already seen that Kruskal's algorithm for minimum cost spanning tree with union find becomes m plus n log n. Dijkstra's algorithm with a heap becomes m plus n log n. Prim's algorithm is very similar to Dijkstra's algorithm. The only difference is that when you take the distance and update it, you are not updating the cumulative distance, but the shortest edge to the tree you have built so far, right? So instead of taking the distance of the current vertex and adding it to the edge cost, you are just taking the minimum of the edge cost, but otherwise it's identical. You have to find the smallest cost edge or smallest cost unvisited vertex to add to your tree. So you can do exactly the same thing that we did just now for Dijkstra's algorithm and implement Prim's algorithm using a min heap and get the same complexity of m plus n log n. So everything is the same as for Dijkstra, because essentially Prim's algorithm and Dijkstra's algorithm have more or less the same structure. It's only the distance calculation or the distance update which is different. And finally, we saw that heaps can be used to sort a list in place in order n log n time. So we have an order n log n sort which is merge sort, which requires extra space. Now we have an order n log n sort which actually sorts in place.